My name is Trevor Branch, and I'm very pleased to introduce to start off the second talk of the 11th Bevan series for sustainable fisheries. The series has generous sponsorship from the Donald Bevan Endowed Fund in Fisheries, as well as from the Alaska Fisheries Science Center and the Northwest Fisheries Science Center. And it's set up to honor the legacy of Donald Bevan, who worked here at the School of Aquatic and Fisheries Sciences for almost 50 years, including a stint as director. The series itself aims to extend his legacy, which really worked at the intersection between science, fisheries, and policy, and was made possible really by his wife Tanya Bevan, who established the fund for the Bevan series. And this year we're looking at a particular topic of interest, which is ocean acidification, and we're looking at the effects of that on fisheries and agriculture. But there are lots of lessons to be learned from freshwater, and that is why we've invited John today, and I can think of no one better to introduce him than someone who has all the dirt on him, and that is handed astray.
Thank you. I promise I wouldn't tell anything that was completely embarrassing. So John Smol did his master's at Brock University in Canada, and his PhD was from Queen's University, where he's been faculty since 1984.
Long time. I know. Falling apart. The grade side of 50 now.
And he's been a Canada Research Chair there since 2001. John has won more awards than I can even start to name, but some of the major highlights have been named the Hertzberg Gold Medal winner for Canada's Top Scientist or Engineer. One for scientist and again, of course. The Hutchison Award winner from ASLO for excellence in the field of limnology and astrology. He won numerous teaching and mentorship awards, including the 3M National Teaching Fellowship, and has recently been chosen by Nature as Canada's top mid-career scientist mentor, which is a huge honor. And this isn't technically an award, but John is commonly known as the science, or the Emperor of Science in China. It's quite more famous than probably anyone else in history. John has published over 400 journal articles, probably another 10 since I started talking up here. 19 books and topics of broad-ranging topics, including climate change, acid rain, historic and population dynamics, eutrophication, contaminants, and drought. And of course, as many of you might know, these are environmental issues that currently face ocean ecosystems, but these have been well known for aquatic policies for a long time, and John has been in the forefront of this research. I've known John for almost my entire academic career, and he's been a real role model to me. Despite having worked on some really challenging and divisive environmental issues, he remains completely positive about science's ability to be the drivers of change. So please join me in welcoming John.
Well, thank you, everyone. I'm delighted to be here. And as was noted, I'm going to be talking about freshwater ecosystems. I'm a freshwater biologist, and I don't directly work with fish, but I work indirectly with fish by looking at the environments that they live in and how they change over long time frames. Also, it's a bit of a memory lane kind of talk. I haven't really given a talk on acid rain for some years. I cut my teeth on acid rain as the first major environmental issue I was dealing with, starting as a graduate student and then as a postdoc, in the early part of my career at Queen's University. So many of the slides are scans of old photographs and so forth, because they're even before digital cameras were around. Just like many of my slides and data have been around for a long time, so has the idea of acid rain. Acid rain has been known for some time. It was in 1720s. It was recognized that rain washed acid and sulfurous particles from polluted air. And in fact, Robert Smith, back in 1872, actually coined the term acid rain. So it's been around for a very long time. Acid rain, however, as a political or as a social issue, really only hit the newspapers in the late 1970s when I was a student. And I remember being an undergraduate or maybe about to start my graduate career, and it started hit newspapers. And of course, whenever something hits newspapers, there's positives and negatives to it. Some of it is identifying an environmental problem. Other things are almost anything that comes up. I can attest that this is in fact true, that acid rain may cause hair loss. I had a full head of hair before I started dealing with this topic. But like most issues like climate change and the associated things that we're talking about in this building and in this university, there are always pros and cons to when it hits the public press by how the scientific information is actually not out there. Well, the thing, acid rain was known as a topic from the 1870s. It hit the newspapers already in the 1970s. Why did it take so long for action? It was in 1990 that the U.S. enacted the Clean Air Act, which cut SO2 emissions. The final NAPAP report, which I was fairly young guy still, but I was involved in as one of the co-authors of one of the sections. That was the National Acid Precipitation Program that was submitted in 1990. And in 1991, Canada and the U.S., was at that time Mulroney and George Bush, I guess the first George Bush, signed a bilateral air quality agreement committing both countries to significant reductions. Still took a very long time. The question one can ask, why did it take so long? Why was this such a politically charged problem? And what did we learn? We now have new problems, bigger problems, I think, much bigger problems. And I hope there's something we can learn from this. Well, and I'm sure this is all review for most of you, but I know there's certainly some students in the audience that may be less familiar with some of the freshwater work. But in many ways, acid rain was both a complex and a simple problem. It was complex because it did things that other problems we hadn't identified up until that time. Most problems till then were local. You dumped phosphorus or nitrogen in your lake, you had a problem. Lake Washington was a good example. There would tend to be local issues. Acid rain had a transboundary type of issue associated. It became more of a, not so much a global, but at least an international problem. Basically 4 consecutive stages, none of which are overly complicated. You need a source of acid. These are going to be sulfur and nitrogen emissions. These are primarily coming from things like coal burning or fossil fuel burning, things such as that. Here was the problem step. There was a transport step, so whoever produced the problem maybe didn't always suffer the consequences of the problem, but it went somewhere else. While it went somewhere else, there was a transformation in the properties, making acidity, and eventually what goes up comes down is the deposition step. And that's where the problems comes. Where does it actually come down? So just to put this graphically, these 4 steps, pretty straightforward. You have emissions, and this is primarily coming from industries such as smokestacks, fossil fuel, much like climate change. Also, every time anyone's driving a car, some sulfur and nitrogen emissions are being released. Then there's this transport step that goes somewhere else by the wind currents. Then there's this transformation. It starts off as sulfur and nitrous oxides. It's converted to sulfuric acid and nitric acid. And then we have a deposition step. The deposition step, perhaps arguably, is the most important one, because where it lands will have very different qualities. It will change the ecosystem in different ways depending on where it lands. The local geology, where it lands on a lake and so forth, all this adds to the complexity. And a lot of the geology came into this, and again, this is, I'm sure, review for pretty well everyone in the audience, but the type of geology, of course, would drive how well the system was buffered or resilient to acid deposition. And if you live in a place like I do, Kingston, Ontario, which has a lot of limestone, it was very well buffered to acid rain. But you just go drive maybe an hour north of where I live in Kingston, Ontario, and you're on igneous bedrock, which has very low buffering capacity, and acid rain could have been a major issue. So local geology played a key role. And it was a complex issue because of the boundaries, because of its moving around and causing problems in different regions. So here's a map of North America showing the major areas of shield bedrock, granite bedrock. So these are the major areas that geologically would potentially be most susceptible to the effects of acid rain. So there's that map. Here's another map. These are the major sources of emissions, nitrogen and sulfur. And you immediately start looking, if you think of that last map, you suddenly realize that the major emissions are in places that really, by and large, weren't negatively affected by acid rain because of local geology, whereas areas that could potentially be affected weren't actually producing much of the acid deposition. Then you add the major wind patterns, you start seeing how you're developing a problem. You put the major wind patterns on top of those last two graphs, and I try and put them all together here, but basically you have a problem. The places producing the acid rain are on geological areas that tend to be relatively less susceptible to the effects of acid rain. You put on top of that the wind patterns, and you have the worst case scenario. You have the wind moving pollutants to areas that are most susceptible to the effects of acid rain, and often to places that did not cause the problem. And this is where you come into all sorts of economic, social, and political issues. People who are making money off of dumping acid rain into the atmosphere are a little hesitant to stop doing that because they're not having the local negative impacts. And the people getting the negative impacts are perhaps not getting any financial gains of using the acid rain. You start realizing why you start having a significant problem. The irony, and I've referred to in my textbook and others, the irony of acid precipitation and why it became a serious international problem, largely because air masses do not carry passports. And once we go now to the next stage of climate change and greenhouse gases, an even worse, more global problem than acid rain. So there's some lessons to be learned there. But here's what the problem is. These are the pH isoplets for this is for the 1980s. This has changed so much. These are isoplets of pH. You can see very different. There's your map of showing the most susceptible areas to acidification. These are the isoplets of that. And if you just look, for example, pH of 4.5, not far from where I live, falling, or the Adirondacks, let's say, on the areas that are the most susceptible to the effects. And this is the irony of acid rain is that basically atmospheres don't carry passports and things move around. Well, there's lessons to be learned from the acid rain debate. So I'm going to describe some of the the actual neolimnological, if you like, data on acid rain, and some of the paleolimnological data to show it was an issue. But I would say, and I think some of the students who are in the class who have read the, I've defined 3 stages in the acid rain debate, which I think we're also having in the climate change debate. These are the 3 stages of denial one might refer to. And the first stage was there is no problem. And we got the same stages with the acid rain. The first thing was simply there is no problem. No one could deny that lakes were acid. Go and measure the pH of the lakes and say all these lakes are acid. No one could really deny that. The arguments were made that there was nothing wrong with these acid lakes, and having acid lakes is a natural part of the ecosystem, and there's nothing actually wrong with that. So first you had to show there was a problem. And this was done in a variety of ways. In this talk I'm going to explore 2 ways. Trevor suggested in some early emails that 2 ways that might be good for this audience is to look at whole lake manipulations, and by that I mean I'm going to go to the experimental lakes area where some of the most definitive work was done on this problem by a massive type of whole lake experiment, and then some of our work that we were closely involved, and I'll be using primarily our U.S. example where I was working with the U.S. Environmental Protection Agency as the lead on the paleo programs for NAPAP. So first of all, let's go first look at to show that there is a problem. First you have to say, define, show that there actually is a problem, that acid acidification causes problems. And we say, of course it causes problems. Well, 1980s, every argument was being thrown out not to do anything, and one of them was that it's not really a problem. I'm going to take you to the experimental lakes area. It's a part of western, we say northwestern Ontario. It's not really northern at all. Ontario goes for many, many hours north of you fly, but anything north of Toronto, I guess, is north of Ontario. But it's almost at the Manitoba border. And the experimental lakes area was a critical area for all sorts of research. And it was driven primarily by this man, where there's some family connections here. Professor David Schindler. David is now currently a professor at the University of Alberta. And although I've never really worked directly with David, he's always been a major role model for me in science and in the use of science. David was a younger man, still a very vibrant researcher. But back then he was, I guess that would be in his late 30s. I'm doing some quick math here. but David was head of the experimental lakes area working for the Canadian federal government. And Dave and his colleagues, a very cohesive, famous group of scientists at the time, limnologists, basically had a license from the Canadian government to torture lakes. I mean, they're not, they could do things that if I did, I would get arrested. And I assume Dave had permission. Knowing Dave, maybe he didn't even have permission. But anyway, the results were worth it. Let me just assure you. What they did is Dave had and his group would manipulate lakes, whole lakes. People at the time were doing things in flasks and stuff. But Dave would do it on a big scale to show, and basically the argument was made, this was such a major issue. We will manipulate one lake with this, for example, in this case, acidification and other torture experiments with eutrophication and else. But the problem is so severe, we can study a lot by manipulating one lake. So what they did is they went to one lake, like 223 in the experimental lakes area. What's critical is, it's out of major deposition. It's kind of like a control site, if you like. And it's also a control site because, well, there's obviously no development around it. It's a pristine type lake. And what the Schindler et al. Group did, after over an 8-year period, they dumped massive amounts of acidification into this lake to artificially acidify it. And they did this between 1976 and 1983. And they gradually acidified the lake from a pH of 6.8, which was sort of its background, down to a pH of 5.0 to show, you do this to a lake, never mind what happens in a flask. You do this to a lake, you're going to see major ecosystem changes. And a lot of detail from this. So this spaceman here, whatever, that's sulfuric acid being dumped away. They put in large amounts of sulfuric acid into the lake. So it's basically 100 years of acidification knocked down to a few years. Sort of Rambo ecology years. Anyway, so then it started. So first of all, you have to need some background. So for about 3 years, they just monitored the lake. 2 or 3 years, they monitored the lake. Then they started adding acid, and it took quite a bit of acid to get some changes. Quite a bit of natural buffering capacity, even in these chilled lakes. So 1974, 75, 6.8 stated backgrounds. 1976 starts changing. They brought it down to pH 6.1. They started seeing subtle changes in the phytoplankton and the primary producers. By 1978, now we're 4 years into the manipulation, 2 years post-background manipulation, they brought it down to 5.9. Then they really started seeing changes in algal species. Very seriously, they saw a major decline in opossum shrimp, Mysis relicta, and the fathead minnow didn't reproduce. So why is that important? Well, here's one of the key ones. Mysis relicta, I'm sure many of you in the audience know, is a large invertebrate. It's not as big as it is there, but you can see it. And it's a major source of fish food. What they were doing is already at this relatively fast, within a few years of starting the manipulation, fish food was dying. Major prey species for the fish were dying. They kept going on. By 1979, now they're down to 5.6. All sorts of ecosystem changes are happening. Filamentous green algae start dominating, especially in the littoral zone. Large sheets, large filamentous growths of green algae are overtaking, which are including some spawning grounds and so forth in the shallow waters. There's a decline in the population of fathead minnow, again, a major prey species. Now the crayfish start showing signs of stress. By 1980, they're down to 5.2. Further changes in algal community. For a while, white sucker actually increases. It's increasing while its competitor is taking advantage of space and resources, while more susceptible competitors are dropping out. And lake trout now start failing to spawn. So if we say like the polar bear is the iconic species in climate change, perhaps, lake trout, salmonids in general, were the iconic species of the acid rain debate. They played a major role in getting public's attention, and that's what people started seeing what lake trouts start doing. And for example, here's this Mugosha, this green algae. You can see overtaking the shallow waters. Never was there before. As I said, there were some short-term winners, including the pearl bass. While the competitors are declining, they're more susceptible, other taxa are increasing, but only for a while. The crayfish, for example, they started seeing increased incidence of fungi on crayfish. Sort of subtler changes, not outright killing organisms, but increase to other types of stressors. And the eggs, for example, here's a female crayfish full of eggs. Very quickly they were seeing, as the pH lowered, the eggs were disappearing and the reproductive success was decreasing. So whole ecosystem scale changes. By 1981, they were down again at pH 5.0 and watching what was happening. More changes in algal communities, zooplankton communities. The whitesucker, which was doing good for a while, now stopped reproducing. Lake trout still not spawning. Crayfish populations about starting to tank. And the prey species for trout are in serious trouble, some of which have stopped reproducing. Okay, well, just to bring the story closer to an end, things just kept going worse. And by 1982, the green algae are abundant. The crayfish are now almost gone completely. Lake trout are on their way out. They're seeing increased cannibalism by 1983. Crayfish by 1983 no longer in the lake, extirpated, and further declines of fish populations. And these filamentous algae are completely overtaking the shallow waters of these lakes. You can see some of the most striking thing perhaps in these iconic species. Here's a picture of a lake trout at 5.4. So it's already getting below its optimal threshold, but still obviously happy, sort of relatively happy, healthy fish. Once you're down here, this is what some of the lake trout we're looking at. So we have a very serious issue happening with the iconic species. And also you can see this in, for example, otolith work, looking at the ear bones. Essentially, you can see the rings. You can see the great reduction in fitness and growth happening right when the acidification hits certain thresholds. So you can actually hindcast this using some of these types of methods. But we have real serious problems happening. So in summary, what did the Dave Schiller et al. Group show? They showed that there's a problem. You start acidifying a lake, you have all sorts of issues happening. You have complete food chain disruptions. A possum shrimp, for example, disappearing very early on, easily stressed, changing the whole food structure. You're having reproduction failures. For example, the fathead minnows. Although the adults might be surviving, they stopped reproducing. You were seeing major habitats altered, largely related, in this case, to that green filamentous alga that started blooming in the shallow waters and completely overtaking some of the spawning grounds. And increased susceptibility to parasites, things like the crayfish story that I showed you there. And I know many of you are interested in fish, and so if you look at and of course toxic conditions, simply organisms just dying. If you look at a broader perspective at the time, while the experimental lake studies were ongoing, people were now starting to do broad surveys of acidification in Canada and parts of the United States, and they were seeing the same things in fish populations, that they could match to what was happening in the ELA experiment. They could show, for example, loss of populations. Some lakes totally lost all their fish. Now, those were typically the more extreme sites. There were some in the Adirondacks. There were some near Sudbury, near the smelters, for example. Complete loss of fish populations, just gone, extirpated from the lake. You see, population size changes, although there might have been, in some lakes, still fish. The number of fish is greatly decreasing, so obviously they're not as successful as they used to be. In other types of lakes, depending on the species of fish and the chemical constituents, the age structure was changing. You would go to some lake and say, oh, there's still big fish. They'd show pictures of big fish being caught. But when they actually did detailed fish surveys, they'd find out one year there were big fish, but they were only 2, 3, 4, and 5-year-olds. Then you go the next year, there were only 3, 4, and 5-year-olds. The next year, there were only 4 or 5, which obviously was happening. The adults were doing fine, but they were no longer reproducing, or the young were dying. So you're seeing this change in age structure over time. And you're seeing some lakes, especially like near Sudbury and so forth, still the total number of fish may not have changed significantly. But because of all the changes in the food web and other stressors, we were seeing stunted populations. The fish were maybe half the size or much lower quality than what we would expect. So the ELA experiment answered many questions that were critical to the acid rain debate. It showed clearly acidifying the lake is a problem. There is a problem. Like all studies, though, it has some limitations. One, the argument could be made, you show problems, but the time scale is totally contracted. I mean, instead of what happens over decades and decades, you do it over a few years. Also, part of the acidification problem, or the acid rain problem, is not just pH. There's a whole lot of other things that happen with acidifying a watershed and a lake. And there's many of these, but one of them is aluminum prepositive, monomeric aluminum. At a certain point in acidification, monomeric aluminum is released from the watershed. and goes into the lake. And some of the biggest problems fish had was aluminum poisoning, basically, because of this increased release of aluminum. If you add acids directly to a lake, that watershed component is not included. Now, that's not a criticism of the ELA work. By doing these more controlled experiments, you can then test the effect of the aluminum, for example. But still, there is still a manipulation like that is close to being a lake system, but it's not all the way. And finally, there's a seasonality to real acidification, and we call it spring shock. Spring shock is acid shock of very low pH waters entering lakes and rivers in spring. What happens is over winter, you have snow accumulate on many of these lakes. That snow is acid snow, but it sits there like a bank just waiting, and then spring comes, and in maybe 4 or 5 days, you can get 6 months of acid rain entering the lake. And so there's a spring shock. There could be this very low pH drop at certain times in the spring. And of course, this can be critical. If you pass the threshold of organisms, it doesn't matter what the average of anything is in the summer. You know, I've had these discussions with some people at the time, and I said, well, you need a certain amount of oxygen. I'll give you all that oxygen for 364 days of the year, but for 10 minutes, I'm going to put you in an anoxic environment. But the average of oxygen will be just fine. You know, I mean, it's the same type of issue. You know, for 364 days of the year, the pH might be enough for the fish to survive. But if it's just 1 day or a few hours that has passed the threshold of its eggs or its young, then it's a serious problem. Of course, it's hard to get that seasonality. So there are some things. So what I'm saying is the ELA experiment probably was a best-case scenario. There are actually a lot of things worse that were going on even than that was shown. But clearly now, stage 1 was gone. So there is a problem, but it's not our fault. And we're kind of at this stage, I think, with climate change. I'm heavily involved with climate change. I think I do a lot of that sort of stuff, and I think we're already past the first denial stage is gone. We're somewhere in stage 2 or 3. Stage 3 is the next one after this, but there is a problem. It's not our fault, and virtually anything that could acidify a lake was being brought up as a cause, and it really, you won't believe it, but just look around at climate change. I mean, all sorts of other scenarios rather than greenhouse gases are being put forward. I mean, here's one on birds. I collect these. I have a whole file of these of all reasons why lakes were acidic. This one, million of bird droppings were worse than acid rain. This was funded by the Hudson Institute, which was funded then by the Coal Industry. But that was a good one. Here's another one I like. Forests, not rain, cause acid in lakes and rivers. This one upset me even more because they were using my data. I have no idea where in my 100 or so publications on acidification did I ever suggest, and I finally figured out where it came. We do 38 lakes. We show 2 are naturally acidic from dissolved organic carbon coming from trees and stuff. So they pulled the 2 of the 38. It's just absurd. And these were, some of these were in major newspapers at the time. So, and again, obfuscating, confusing the story, and so forth. So we had problems. So we have to show that's the cause. So the questions at the time, have lakes acidified? No one could deny acid lakes were causing problems, but have they acidified? If so, when and by how much, and what caused the acidification? The cause was a key factor, and this is where the real problem is. We didn't have the long-term data. No one was measuring pH on the long term. Keep in mind, Sorensen only invented the pH function in 1909. We need to solve this problem, because acid rain's been around for about 100 years. You would have to know what the pH or the water chemistry of the lakes were like in the early 1800s, before acid rain was an issue. We didn't even know what the pH was in the 1950s, let's say. We certainly didn't know what it was like in the 1850s. This is where the real problems came, and this is where a lot of our work came in. And I summarize it by saying the past matters. History is important. History is important in a lot of things we do in politics, in society, and so forth. It's important in environmental issues. Every environmental issue has a history. Often in that history is where many of the answers lay hidden. And that's where my work, my specialty, I'm a limnologist, but my specialty is paleolimnology. And paleolimnology can be described as reconstructing lake and river histories using the physical, chemical, and biological information preserved in lake or river sediment cores. It looks like a science that is a leap of faith. I can think of hundreds of reasons why these methods should not work. Having said that, the methods are much stronger than they would first appear by looking at it critically. Because we use so many indicators, and I'll talk about this in a few minutes here, the amount of information, there's so much self-correction in the data, we get very strong inputs. So what is actually paleolimnology? Well, it's pretty straightforward. Lakes slowly fill with sediment. 24 hours a day, 365 days of the year, sediments are accumulating at the bottom of the lake. That sediment comes from a variety of sources. It comes from allophilous material coming from outside the lake, things like pollen grains, contaminants, soil particles, as well as autochthonous sources, things from inside the lake, dead algae, dead invertebrates, chemical precipitates, and so forth. All this is making its way into this history book at the bottom of the lake. Our job as paleolimnologists is to remove that history. Things are slowly accumulating over time, and to use that information in a way that's meaningful to other scientists, politicians, and the public at large. That history book, that library of information, is surprisingly complete. It was not long ago, when I was starting my career, that we thought maybe diatoms and pollen grains, but now we know virtually everything living in that lake is leaving a reliable record, either as a morphological indicator. By morphological, I mean you can see it under the microscope, or more and more we're now finding of a sort of a biogeochemical indicator, whether a fossil pigment or some form of organic geochemistry and so forth. But we can track almost everything that lives in that lake using some form of indicator. Our job is to reconstruct the lake's history and to use the ecology that we know of all the indicators we find in those sediments to reconstruct environmental change. Just give you a few slides of how we actually do that. A lot of this equipment was developed by John Blue in my lab during the acid rain issues. This is kind of a new area of paleolimnology. Up until then, paleolimnology was mainly looking at, since the Ice Age, what happened, long-term ontogeny. We were going to use the surface sediments to use high-resolution reconstructions of environmental data. First, you've got to get the history book. And to do that, you need a high-resolution core. These are fairly simple cores, called the blue cores, named after John Blue. Quite simple devices, but they take, even with over 95% water surface sediments, you slowly lower these gravity cores on that rope into the sediments. And you send down a messenger, much like putting your thumb on a straw in a milkshake or something. You pull it up, and you can get the surface sediments extremely well preserved. You can see, I don't know how long this here, this has to be a bar link and actually the layers. But and for most lakes in, say, Washington or Ontario or New York State, 50 centimeters would be about the last 200 or 300 years of the lake's history. There's the history book. Then what do we do? Well, that's the book, but how do you turn the pages? Well, again, fairly simple equipment. These are the glue extruders. Here I'm extruding a 1/4 centimeter at a time. For most places in, like, say, Adirondack Mountains, where I'll use some of my examples, a 1/4 centimeter is about 2 or 3 years of the lake's history. Now, how do I know it's 2 or 3 years? We're not really just guessing at the dates. There's a variety of dating methods that we can use. Especially for the last 150 years or so, we use lead-210. Lead-210 is a naturally occurring radioisotope, has a half-life of about 32 years. We take each sediment slice, we measure how much lead-210 is there. Since we know its half-life, we can set like a clock, a geochronological clock going back in time. For older material, we use radiocarbon dating and other methods. There's quite a few dating methods, but lead-210 is sort of one of the workbooks. And so this is a core taken in 2006. We can lead-210 data, we can say that level is approximately 1846, that's approximately 1926. So we can sort of paginate the history book. Then we can section it, and we look what information is there. There's a tremendous amount of information in the sediment. There's material coming in from the atmosphere, and I'm only going to talk about a few of these. But for example, there's the actual products of combustion. There's carbon particles from carbon combustion, fly ash from coal combustion. There's specialists, including some who've gone through my lab, who can look at these particles and not just tell you it's coal or oil or wood, but they can even tell you by looking at it microscopically and doing isotopes geochemistry, tell you what it was. To some extent where it came from. That's even products from Venezuelan oil, or that's something that was burned probably in China and so forth, by fingerprinting what the burned product is. There's a whole spectrum of geochemistry metals, lead, mercury, cadmium, all that, persistent organic fluid, PCBs, DDT, all that is making its way into the sediment history. There's a lot of material coming from the catchment. Things like pollen grains. All the trees out there produce different types of pollen grains. By looking at the pollen grains, we can reconstruct how the terrestrial vegetation has changed, from which we get ideas of climate change, human impacts, and so forth. a very, very large part of the field. Mineral particles for like erosion, insect remains, all that's making its way into the history. Now, I'm a limnologist. I'm more interested in what's actually happening in the lake itself. And so I'm typically more interested in organisms and indicators from the lake. I'll talk to them as indicators. Foremost among these are going to be algal indicators. Especially in acid rain, the algae were a critical role. And diatoms and chrysophytes were the two lead organisms. I'll talk a little bit more about diatoms because they make a big part of the story. But virtually everything living in that lake is leaving some sort of record. And it's not just the algae, all the invertebrates, the chironomids, and at the very end I'll bring you some invertebrate work talking about multiple stressors. But virtually everything is leaving some sort of record. So, but a key player is always the diatoms. I'll say a little bit more about them. I'm sure many of you know quite a lot about diatoms, but diatoms, or the Bacillariae phyceae, is a major group that we work on in my lab. They're extremely abundant. There's various estimates, but a very large proportion of this Earth's production is coming from diatoms. Almost anywhere we have water, whether it be salty or fresh, or a river or a lake or an ocean, diatoms are often the dominant form of algae. They're extremely diverse. There's tens of thousands of species, and so they're extremely diverse and successful group of algae. They're excellent environmental indicators. Different diatoms live in different environments. Some live only in very fresh water. Some live in salty water. Some live in only very acid water. Some live in alkaline water. Some live in shallow water, deep water, and so forth. A large part of what my lab does is to catalog, using very robust statistical techniques, ecological optima and tolerances of these hundreds of species that we can then use to reconstruct past environmental changes. And very importantly, they have glass cell walls. So they're very well preserved in lake sediments or ocean sediments, especially lake sediments. And this is what diatoms look like. I'm sure many of you know them. This is a figure from my textbook. But, you know, so I can see a cyclotella like this taxon here. I know that's a nutrient-poor, cool water environment. I see there's a Lacosaira. That's from an environment of higher nutrients. This cymbella is found only in very shallow waters, living attached to aquatic macrophytes. These are the types of things that are cataloged, not just in a qualitative way, but in a quantitative way in many of the databases that are in places like my lab. And I'll show you how we did that with acid rain. But when it came to acid rain, we wanted to use paleolimnology for two things. Remember that challenge, have lakes acidified? If so, when, and by how much, and what caused it? You need the time frames. So what we wanted to do is reconstruct targets. What were the acidity levels before acid rain was an issue? What was the pH of these lakes in the early 1800s? And secondly, trajectories. If pH has changed, what is the direction of change and the speed of change? And at what point in the amount of deposition falling did we reach a critical load where we really had an ecosystem problem? And I'll take you, we did this work all over Europe too, North America. But I'm going to take you to the US EPA funded work, which is in the Adirondack Park, just south of where I live in Kingston, Ontario. We had a 5-year project there. We did the second half of NAPAT, coordinating all the acidification work there. And the Adirondack Park, a beautiful area, as you saw that last slide, wilderness area of high acid deposition. This is sulfate district, so it's receiving lots of acid rain. So here's our study area. Those are the dots, those are the lakes we worked on. We worked on a large number of lakes, about 80 lakes in all. So we had a very good survey of lakes in the Adirondack Park region to do these analyses. And the first thing we had to do was develop a pH meter, a paleo pH meter. So I said different species of organisms live in different environments. Turns out pH is one of the major driving forces of which species of diatoms live in what type of water. How can, I can look at a diatom, I know that's an acid species, I know that's an alkaline species. That's not going to get legislation. The question we were always asked when I was going to Washington and so forth is, will the lawyers buy it? And it was basically, will it stand up in court? And so a large part of it was in developing the actual method. And what we did is a fairly straightforward one. We used surface sediment calibration sets. It's fairly straightforward. I'll use the Adirondack example. We had 82 lakes, I believe, in the Adirondacks, which were very well studied. And so we had a very good environmental database. We had 82 lakes. We knew what the pH was for the last 2 or 3 years. We knew what nutrients were. We knew what depth was. We had a very good environmental matrix over the last 3 years for these 82 lakes. That's one data set. We then went to each of the 82 lakes. We took a sediment core from each of those 82 lakes. We removed the top half centimeter. The top half centimeter represents the fossil, the algae, the diatoms that live there over the last 2 or 3 years. We counted by different species. There could be 100 species in some of these lakes, but percentages of 20% of cyclotella, so we had a species matrix. It doesn't take too much to put those two matrices together with some statistical treatment and to sort out where the taxa are most common, to look at their species optima. So if this is pH here, let's say we're looking at chrysophytes in this case, this would be something like Malamonos hindonii, not only in very acid waters. This is something like Cyanura perdispina, not only in alkaline waters. This one with a circumneutral or broad curve would be something like Malamonos crassisquama, the generalist, and pH. We do this not just for 5 species, hundreds of species. The curves are not as beautiful as that. They're a bit messier, but there's so many of them. There's hundreds of species. So the final transfer function is quite strong. This is just on chrysophytes. And I think you'd agree this is chrysophyte inferred pH from the surface sediments. That's actually the measured pH of the water. And I think you'd agree, and this is for chrysophytes, the diatom functions are even stronger. If I knew what the fossil chrysophytes were, I'd have a pretty good idea of what the lake water pH was. So we developed a paleo pH meter. Then we can use that going down the core. So this is what some of the profiles look at. This is deep lake. The very first paper I published in Nature on this was the very first chrysophyte profile showing acidification in the Adirondacks. And even if you know nothing about chrysophytes, something obviously happened here. Let's take a look at it. So this is the core going back in time. So it's 1980, telling you how old this is. That's 200 years ago. So that's lead 210 dated. These are the percentage of the dominant chrysophytes. Very clearly, something remarkable happened in the 1940s. Before that, we had these circumneutral, I know there's circumneutral, I know these algae very well, Malamonos punctifera, circumneutral chrysophytes here, slightly acidic chrysophytes. Then something remarkable happened in the 1940s. Almost 100% shift to these very acidic species. I can say that looking at it, knowing the ecology, but then I can put it through those transfer functions, and you can actually get a pH reconstruction. So you can say the pH of this lake was somewhat naturally acid, around 5.5, which we learned was common in some of the lakes, and then you can see that remarkable acidification starting in the 1940s. That's a lot of work. You do that, US EPA wanted to know this for about 40 target lakes. They had chosen 40 lakes on a stratified kind of design, and you can bet they chose them, because I would have never chosen how hard it was to get into some of these things. But that's why you have grad students, right? But anyways, I would have chosen much easier. Something right by the road would have been good for me. But anyways, they chose it because these were like representative lakes of the whole system. And they wanted 40 lakes done, 42 lakes I think it was, done in a fairly short time. And this is a lot of work sitting at the microscope. So we developed a shortcut method called the top-bottom approach. And Glenn is wearing a bathing suit. I just saw this. These are all slides. I just said, he is in fact wearing a bathing suit. But anyways, the top-bottom approach is instead of doing perhaps 20 or 30 slices for each core, which can be done, but is a significant effort of, each slide on the microscope is at least 3 hours and so forth. The top-bottom approach is a shortcut. It's a before and after. What do? We don't do 20 or 30 slices from a core. We do 2. We do one at the very top to represent present-day conditions, like the calibration. And then we do another one which we know is pre-1850, before acid rain. And we look at the diatoms or chrysophytes or whatever indicator we're using. And we reconstruct the pH pre-1850. So instead of having a whole profile, you get 2 points. It's a before and after kind of assessment. And so we did that on these stratified lakes. And this is a somewhat complicated slide, but the lead was Brian Cunning, who's now the co-director of my lab. He was a student at the time. These are I believe there's about 40 lakes here, ranked in present-day pH. Wolf Lake, very acid, 4.4. Chunk Lake, circumneutral, 7.8. There's a lot of data here. Let's just look at change in pH. What we're looking at here is the change in pH since the 1850s. Now remember, Sorensen only invented pH in 1909, so we're reconstructing pH from the early 1800s to the present. If it goes to the red, it means it's acidified since the 1800s. As you can see, every single lake below a current pH of 6 has acidified since the 1800s. Some of them by over 1 pH unit. There's a remarkable amount of acidification. You'll notice the lakes that are currently on the alkaline side have little change, and in fact, slightly increased in alkalinity. That's exactly what the modelers and the biogeochemists should happen. That's what the monitoring showed. Acid rain falling on calcium-rich environments actually increased slightly in pH. So this is exactly what we would have predicted. This is acid neutralizing. We have 4 functions with the diatoms. This is acid neutralizing capacity. It shows the same pattern. Monomeric aluminum, remember I mentioned, can kill fish. We had a weak relationship, but still a relationship with the diatoms and monomeric aluminum. As you can see, monomeric aluminum greatly has increased in the acid links. Dissolved organic carbon, a source of natural acidity, shows no real pattern. So this showed, yes, the lakes acidified. They acidified since the 1800s, and many acidified to a great degree. I just took those data and put them on a map of the Adirondacks. Again, I'm sorry, these are scanned, because these are photos before you even had digital images. This is a map of pH. These dots make various lakes, background pHs of what the Adirondack pH map would look like in the 1800s. I'm not sure how well you see this, it's a scanned photograph, but none of them are very acid. Some are somewhat acid, 5 to 5.5, and this is where the trees cause more acid rain came in. But there's very little pattern, but none are very acid in the 1800s. This is now the same map showing the change in pH since that time. And these are enormous pH changes. This is like 1. Here you see a pattern. You see a lot of acidification, and a lot of acidification. You know, these are like 1 pH or more, these darkly red side. A lot of acidification happening, especially in the southwest part of the lake. This is geologically the most sensitive part of the lake, because of the local geology. Most importantly, I've superimposed isoplex of precipitation. The areas receiving the most acid deposition also acidified the most. So, the general conclusion, that's 5 years of work in 2 slides, but acid-sensitive lakes in the Adirondack Park have acidified. We know that from the top-bottom buddy. We didn't get, but since it was just that shortcut method, we couldn't say when they acidified. So this required more detailed work. So the next stage was when they acidified, at what level of acid deposition did lakes begin to acidify, and what are the critical loads. Basically, the next question is, okay, we agree the lakes have acidified. We agree humans are there as the factor. But obviously, we need to now know how much do we have to cut back before we have a problem. And that you need critical loads. And so critical loads is the highest load of a pollutant that will not cause changes leading to long-term harmful effects of the most sensitive species. So how could we do that with Pianco? Well, we needed time. We knew what past deposition was. This is the work for Guzar and others. This is not paleo data. I'm going to say it's real data. Paleo data is also real data. But this is actually working out what the smokestacks were like, how much was being burned, and you can see that is the stressor. That is how much sulfate deposition has been falling on the Adirondacks. Slight dips during post-war periods and stuff, but this is the amount of stressor. If we can get the same thing for pH, then we can find out at what point of sulfate deposition is there a problem. Well, to do that, we can't do a top-bottom. We have to go and do detailed analysis. We did that for, and again, a set number of cores, and I'll just go over this very quickly. But this is a summary diagram. But basically, we look, and this is just chrysophytes. We show when the lake acidified to a certain point. You see those acid species coming in. And then we could, this is the Guzar curve I just showed you of the stressor, knowing what the sulfate deposition is. This is the reconstructed pH showing that big acidification in this lake around 1950. We could simply show when the lake really acidified to find out what the loading was, and the critical load we would say for this lake was 25 kilograms per hectare of sulfate per year. You can do that for a large number of lakes to get at critical loads. The only way you can get that is really high. You can either hindcast or you can model it. Both have issues. When the model forecast and the hindcast and the paleo data merge the same answer, I think you have a much stronger case for all. So it shows that many lakes had acidified, but that lakes responded differently depending on buffering capacity, flushing time. So it was a complex story. And the question many of you might be asking is, so what? Who cares what diatoms do? What about the fish? That's what a lot of the public wants to know. And this is where the challenge comes. We knew there was very good fishing in the Adirondacks. Fisher people were saying the fish are decreasing or disappearing, or there were like fishing camps on lakes that had no more fish in them. What was the cause? Was it overfishing? Was it people taking too many fish? Was it acid rain? The problem with paleo data in lakes is that fish fossils are tough to use. There's not that many. There are bones, there are fish scales, there are ossolates, of course, but there are issues with fish fossils. Just not that many to get a real representative number. What we can use, however, is indirect fossils. Fish food, different types of fish food, and what can coexist with fish and what can't. And there's several species we can use, but the main one is Chiobris. Chiobris is the phantom midge, or sometimes called the glassworm. This is the invertebrate stage of this fly, the larval stage of this fly. The whole fly larvae does not preserve. The head capsule preserves, and only part of the head capsule, the mandible, part of the mandible preserves. But fortunately, different species have different mandibles. So the part that's preserving is, again, species specific. There's 4 main species in the Adirondacks. And fortunately, again, one of them, Chiobris americanus, can rarely coexist with fish. So once you start seeing Chiobris americanus mandibles in the fossil record, you have a pretty good indication all the fish have died. Now, it's a blunt tool. It's not telling me when the trouble died, but it's a yes-no kind of answer. And we can then, now since we know the pH has changed, if we know when the fish died, we can start putting it together. This is some of the work of Al Lugla from a postdoc of mine. We summarized it in this review article, but here are 3 Chiobris curves for 3 lakes in the Adirondacks. Here's Windfall Pond. It always had fish. It never had Chiobris americanus. It always had fish, never acidified, not a problem. Here's Deep Lake. That's the example I showed you earlier. Deep Lake, the one that greatly acidified. Look what happened. When the lake acidified in the 1940s, look what came in. Chiobris americanus. Just as the lake dropped its pH beyond its critical level, it became fishless. What about Upper Wallface Pond? Upper Wallface Pond, one of the few lakes we found that had Chiobris americanus going back thousands of years. It's always been fishless. It's also one of the lakes that appeared to be naturally acid. It's probably developed organic carbon going back in time. So, here's a lake that's naturally acid and naturally fishless. This is not a good candidate for fish stocking or for liming. They did both. The background conditions are important in fish mitigation and things like that. We should know what it's like. It is nothing natural about stocking a lake that's been fishless for 12,000 years. That ecosystem has developed as a fishless environment. Of course, it never worked. But to come down to the last stage. So, there was a problem. There was a problem. Not our fault. That didn't work anymore. I think I was pretty clear. There is a problem. It is our fault. And now it's too late. There's nothing we can do about it. Sadly, I think we're getting somewhere between stage 2 and 3 in the climate change debate. But in the acid rain debate, what we had to do then, this really came up, said, okay, yeah, but it's too late. Lakes are acid. Then we had to show they can recover. And this was done in a variety of ways. In ELA, they did it by stopping the acidification, or letting it recover. By 1984, the pH increased to 5.43, and that's what it looked like with pH 5.1. By the time they were back to 5.43, the trout were coming back, so you could show a recovery. We could do that. I could talk a lot about recovery in paleo, but this is in Sudbury, which of course had a major source of emissions from the stacks. There was dramatic Ontario changes in emissions, and you can see the remarkable recoveries going back to pretty well pre-impact conditions when they cut down emissions 90%. So we use paleo to show, yes, if you do something, something does happen. But just to conclude my last few slides, it's like a happy story. I mean, in some way, not that happy, but it ended with legislation, and lakes are slowly recovering. I mean, in some ways, acid rain is a partial success story. The problem is, something we have to learn in climate change and all other things, nothing's as simple as we think. There were problems we didn't even know, and we're only identifying now, 20 years after the debates, of what the problems are. Nothing is as simple as it seems. And what I'm talking about is the threat of multiple stress. So I'm just going to conclude with a few slides here of some very new work. And what I'm really talking about is the problem we call aquatic osteoporosis. And that's the widespread threat of calcium decline in lakes. Just pulled this, I guess now a couple of years ago in Science, in November, December 2008. Adam Jaworski, a PhD student in my lab, is the lead, and Norm Yan was a key player, professor at York University. We published that in Science a few years ago. And it was a problem that was completely under the radar. It shows the value of long-term data. This is the Dorset, some of you may know, the Dorset Ministry of Environment Environmental Station. It's been monitoring lakes since the 1970s, 1977. They have the so-called A-lakes. These are lakes they monitor every 2 weeks. They've been monitoring the same methods going back 30 years or so. No one was paying much attention, but Norm Yan started looking, and Andrew Patterson, a former PhD student of mine, was just started plotting some of the variables going back 30 or so years. And he said, look, what's calcium doing? These are the main lakes, the so-called A-lakes, the ones that are really monitored intensely. calcium, you know, little bits of, when you look on the long-term data, the calcium levels are dropping and dropping and dropping and dropping. What the heck's going on? It turns out this is a serious problem that is related to acid rain. Calcium is required by everything. I mean, we require calcium. It's required by algae, required by invertebrates. And different organisms have very different calcium requirements. Some have very high. They have a high calcium demand. And like some invertebrates, only get their calcium from the water. It's not their food. And how to say that? I mean, it's a very basic diagram here, but you know, at least the calcium's in the soil. And where does it come from? It comes from some atmospheric deposition, and it comes from mineral weathering. This is a very slow process. But for thousands of years, there was some calcium was always slowly weathering into this pool, and some of that was leaching into lakes, and some of it was going into trees and vegetation, and everything seemed to be in balance. Then we started doing something. We started an uncontrolled experiment called acid rain. We started dumping acid rain on this thing that's been working since the last ice age quite nicely, and it's more or less in balance. And what did acid rain do? Well, for a little while, acid rain would greatly accelerate the leaching of calcium from the land. And so for a little while, there'd be a whole lot of calcium coming into the lake because it was leaching out. But eventually, this exchangeable calcium pool would be declining, 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 and eventually, there'd be less and less of it leaching out. On top of that, we're also doing forestry in the same basis. Every time you remove trees, you're basically exporting calcium. There's a lot of calcium in the bark and trees. You take that, you're basically taking the calcium from the watershed and you're putting it in your house. Well, new trees come up, and they're sucking up more calcium from the ground. The net result is that calcium is decreasing and decreasing and decreasing in your environment. This is the problem. We saw that long-term trend in the water chemistry of these 5 or 6 lakes. Was it a real problem? We needed some indicator to see, are we losing calcium? Diatoms won't work. Diatoms don't need that much calcium, and they don't do it directly. We needed something like a miner's canary, something like the coal miners would bring down, and as an early warning indicator. And what it came down to, it looks like the crustaceans opine, especially the Daphnia. Daphnias, I'm sure many of you know, or the various different types of podostras, are completely dependent, direct dependence on calcium. They use a structural material for the carapace. And they get their calcium from the water. When they molt, they need more calcium. They go through these series. So they have really high calcium. It turns out that different species have very different calcium demands. This started off by work by Norm Yan and Adam Jaworski at York University and others working in Europe in flasks showing different species of Daphnia, different species of Bosmina, and these different calcium requirements. They also then went into the field, so yes, sure enough, you can start showing these trends with calcium in these different species. And it turned out that we probably have a very good indicator. Different species of Podostra have very different calcium requirements. Some have quite high calcium requirements. And importantly, these invertebrates leave very good fossils. Their exoskeletons can be identifiable often to the species that are in the lake sediments. So we have the indicators. We have everything going. And it turns out, this is a long story, but I'll make a long story into one slide. By looking at field studies, lab studies, control studies, certain species had real thresholds to where they couldn't reproduce. And it turns out the large Daphnia pulex and so forth, cannot reproduce below pH of below 1.5 milligrams per liter calcium. Others, like the small Daphnia of Bosmina, do very well even in low calcium environments. So we had a whole spectrum, just like we showed with pH, we had with calcium. Daphnia, these large Daphnia appeared to be the key. I'll show on one slide 3 profiles to show this is a serious problem. I'll show you 3 different scenarios. Plastic Lake in Ontario. These were all lakes with low calcium, below that 1 point, at or below the 1.5 laboratory threshold. Plastic Lake received acid rain, but lake hardly acidified, maybe 0.1 of a pH unit. We had that from the paleo data, we have that from the monitoring data. We also have long-term calcium data in this lake, so we can ground truth it. Little Willis Lake, Nova Scotia. Nova Scotia, famous for its naturally acid lakes, natural acids. It's always been an acid lake. pH has not changed, yet calcium has been known to decline over the last 20 years. Big Moose Lake, the third scenario, a lake that greatly acidified in the Adirondacks and then recovered with the new legislation. Yet calcium continued to decline. It just was so depleted, never increased. So we have 3 scenarios. All of them decreasing calcium, one never acidified, one always was acid, one acid and recovered. What did we find? And we have detailed diagrams of many of them, but just showing you these 3. All 3 show quite clearly at the time of calcium decline, great drops in Daphnia. Now, you might ask, how is the fish and so forth, top-down control? Those are exactly opposite changes that you should be expecting now with top-down control. This appears to be closely related to calcium, and we have this from many lakes now happening. We appear to have the indicator fluids. How serious is this problem? We found in this paper 770 lakes across Ontario that there's data going back to the 1980s of calcium and pH, and about 1/3 of the shield lakes now have declined below that threshold, and 2/3 are almost at that threshold. This is a very serious problem that is affecting these lakes. So who cares if Daphnia disappears? Well, you know, a lot of things, because Daphnia is a key member of the food chain. A lot of things eat Daphnia. Daphnia is a big regulator. It's a keystone species in many of these environments. And if Daphnia is in trouble, what about all these other organisms that even higher calcium? You see crayfish disappearing in some Algonquin Park lakes. No one knows why. Is this now really a calcium? Something under the radar. It was one of those side effects of the story. So maybe we were looking for the miner's canary for calcium, and maybe the limnologist miner's canary might be finding that. Just to conclude, there are, I think, many lessons from the past. And I think one of these is the recurring pattern of unintended consequences. I think the calcium decline story is just one of the many examples I could have shown you about. History is full of this. And in anything, we tend to be overly optimistic. Things are generally much worse and more complicated than we initially imagined. And we're dealing with multiple stresses. We're like reshuffling the cards. This is not easy for us to deal with. We tend to, even in our subject areas, tend to deal with one problem at a time. And even when you look at research groups, we tend to be, well, you know, we're looking on acid rain, or we're looking on climate change. But now we're realizing we can't really do that. Things are happening all at once. And sadly, almost always, the synergistic effect, I mean, it's a bigger problem when you put them, even when additive. Sometimes it's like multiplicating. It's a very, very serious issue. So, and we're just finished with this slide. Do these three stages sound familiar with the climate change debate? And I think there's lessons also to be learned on policy, and lessons to be learned on how we actually deal with these issues, bringing the science forward. I think we're seeing the identical three issues now with the climate change debate. And I think we shouldn't fool ourselves. We have an uphill battle because we are bringing in bad news, and that makes it much more difficult. Well, thank you very much for your attention.
There's time for a few questions, and then there'll be a live reception afterwards. So I'll leave questions for 10 minutes.
Yeah, and could you say some words about what the relates with
in lakes? Yeah, I don't think the effect is happening in lakes. I think the buffering, the effects of deposition is far outweighing anything that would be happening right now with the CO2. What's happening in the oceans. So I don't think we're seeing that. I think with that little effect that is, it's marred by all the other sources of deposition in these environments. We're dealing with relatively large, small volumes in many of these lakes.
all the way out to the end of the century? CO2 800 parts per million?
Oh, I don't say 800. I can't get my head around 400, but anyways. It's, you know, we're going to see so many other problems before then that I actually didn't look at the chemistry that closely, but I'd like to look at that, but I'm not sure. I think, frankly, in lakes, those pH changes that you're seeing in the ocean are subtle, because we have even daily fluctuations in that pH range, which is higher than that. Lakes are quite, I think, far more dynamic in some ways, even on a diurnal basis than that. So I think it's a lesser effect there. It's a long-term trend is what we're able to.
You talked about recovery of some species as the pH went back up, and I was wondering if there are any cases where there's data on what might be different in the recovered population genetically or otherwise.
Yeah, it's a very good question. I went through recovery very quickly. I should say chemical recovery is being seen, and by that I mean going back to the original pH we think. We are also seeing some biological recovery, but not anywhere nearly as clear as the chemical recovery. First of all, you know, extinction's forever. If you drop something out, they're not coming back. And also, you know, if the fish are extirpated, just getting them back in is an issue too. we are seeing changes in biology, but they're not going back, like the diatoms are not going back to the same diatoms that were totally same assemblages that were there before acidification. They're indicating a similar type of pH. So it's not a real full biological recovery. There's a lot of filters to that biological recovery, but not least of which we've changed the palette. You know, the climate is different, the stratification is different, the ice cover is different. This is why it's very hard to disentangle. Is it still just because of some chemical reason, or is it because the climate has changed and all the other problems? So biological recovery has been far weaker than the chemical recovery of these acid lakes. In some places, we haven't seen really anything, a recovery to what was there before. We're seeing a recovery to an assemblage that is more circumlutional, I'd say. So it's, for conservation biology, the news isn't as good as the chemical biology.
Biologists start to wake up and realize that we're hearing about ocean acidification, and there's this growth industry, and we're left with the question of what are the biological responses in the ocean going to be to the acidification? And you can't do whole ocean experiments.
No,
so
your dad might try, but anyways.
The approach people are using is taking individual species, putting them in highly controlled environments, acidifying them. I guess I'm asking for a comment. You know, that lake acidification research 30 years ago was using exactly the same approach. And I guess the question is, how well did that type of approach play out in terms of our ability to assess how the systems respond?
That's a very good question, and of course a major challenge to the ocean community. As Dan says, both the eutrophication before my time and with acidification, a lot of the early work was done like in flasks and in laboratories, which of course tells you something about the physiology of the organisms and so forth. But many of the early results were quite contradictory to what we found out to be true. That was definitely true of eutrophication, where you can almost show anything, with the right conditions. There are hints, we get hints and clues in the flasks, but it's very hard to actually mimic what happens in the lake. And so I think there's a progression of, let's say flasks at one level. Next might be mesocosms, which of course have their issues too, but you kind of take part of the ocean or part of the lake and try and deal with that as your unit. And of course, in the whole lake system, or whole ocean system. The best you can do, I think, in the ocean is comparative, but that's very difficult, I agree. There's real major challenges in the ocean. And Dave Schindler and his group showed quite clearly that what you can show in a flask is no doubt under controlled conditions what's happening in that flask. But the relevance to the lake could be challenged very quickly as to what actually happens with something that's overturning and is actually 30 meters deep and has an ice cover in winter and all these things that you don't really do in your 4-week experiment. Having said that, there's a lot of things you can learn. I mean, our calcium work was to some extent started by flasks, finding out, growing Daphnia, and, this is not me growing, but Adam and Norman and those, growing Daphnia and Cladostra in different defined environments and so forth, finding what the things. So there's certainly a lot of information there, but when it comes down to the real ecosystem consequences, it's tough. And even the ELA experiments, as elegant as they were, still underestimated how bad the problem was. We're often just showing best case scenarios when we think we show a really bad problem. It's totally, we didn't bring in all these other problems that were happening that were completely under the radar screen. So, I mean, it's quite depressing. You are dealing with ocean acidification, a very complex issue that's going to be even more hard to show, display, solve, I think, than lakes. We thought acid rain was very complicated at the time. Now it's just, ha-ha.
You mentioned the lessons learned from the acid rain on how to present the science.
Yes, that's a very good question, very good point. If we learn anything about how to present the science, I think that's critical. I think we're doing a better job, but we're still doing a very bad job of getting the science out there. And there's many blocks in our way. It's not just that we're lazy or incompetent as scientists to do this. Though there's a bit of both of that. I don't mean lazy, but I think something we have to do as science, I think, me speaking personally, spend much more time explaining why we did it, why it's important, and what's the significance of it, and why it should become a bigger part of the policy pie. We seem to be quite content to sit there. I just can't imagine how small science is in the policy pie decision making, but how much are we actually doing to change that? The onus is on us to do that. And the onus is on us and nothing else. The public paid for much of what we're doing, and they deserve a better shake from us. The other way is we have to, I think, learn better ways of doing it and realizing that we have an uphill battle. When you deliver bad news, it's not the easiest message to deliver. When the people in a democracy who make the decisions, make their decisions on a completely different time scale than we deal with, that's another challenge. Many of the problems I'm talking about here took decades to become a problem. Climate change is, even on a longer time scale, if you like. Politicians at best think on 4-year cycles, at best. Industry, who sometimes you have to convince, at best seem to think about quarters, 90-day cycles. We are dealing on very different timescales, which is one of the first challenges. And that is hard to get across. I often sometimes compare environment to education. It's hard to get governments to invest, frankly, in those because if you like, the profits from this, whether environment or education, are often 10, 20 years down the road. Not in my political mandate. I'm going to spend money and not get basically credit for it. Education, same thing. It's a way that improves things. It's complicated further by how we get information out. The media is a typical way most people get their science information. We're not really that good with talking with the media. I think that's one issue. The media, I think, there has to be some more discussion of how results are presented to the media. There is the sort of the fairness doctrine that came in with television back when television became popular. It basically came up if you give basically the Republican side, you give the Democrat side, which is fine, I think, in a political debate. I'm not sure every scientific debate has to go the same way. Opinions don't meet very much in science. Data matters, evidence matters. And I'm not sure that every time I'm talking about the latest disaster coming from climate change, the media in Canada, and I think here too, feel compelled to have next to me or next to you someone saying that it's, Elvis Presley or something causing it. Or it's absurd. I mean, and yet it's presented as, well, there's a very serious debate going on here. And of course the public then goes to a very serious debate and there's no consensus. First, there's no consensus on anything, but there's reasonable consensus. I mean, there's reasonable consensus that tobacco is not good for your lungs. The data on climate change, I would argue, is far stronger than that. But yet, we don't really, it's still seen as has to be presenting both sides. And I even talked to me and says, now can you suggest someone who disagrees with you? And I said, well, I can, but I don't really want to. Right? I'm happy to disagree on the science if it's a serious scientific question, but and it is confusing. I mean, and of course, and now anyone with anyone with an internet connection is a publisher. I mean, it's just gone bizarre. There's no filters to what's out there, and so most people get their information on Google searches. Well, put down, you can look up anything and get all sorts of, so it's really controversial. Well, how come something written on a personal website has the same value as a paper in Science or Nature? Then you have a problem. So, big challenge. It's not a simple story ahead of us.
Any chance for one more question? None.
So
we get a
Thank you.